Okay, hello. Yes, my internet. Good afternoon, Brian. Thank you for being so prompt. Okay, good afternoon. Okay, hello, direct chat person. Also, thank you for bringing prompt. Good afternoon, Natalie. Good afternoon, Ellie. Good afternoon, Gabriella. Good afternoon, Kaya. Good afternoon, Genesis. Good afternoon. Ariana, good afternoon, Carlos. Good afternoon, Sydney. Um, okay. I'm a l- so we have two more classes, including today. Good afternoon, Mariam. We have two more classes. I have to warn you right now that, so I have big ambitions for these last two classes, but right now, and good afternoon, Annie. But right now, just to warn you, we seem to be okay, but I have to tell you that all of the power and internet is out in my house. So right now I'm doing this from, not that you care, but I'm doing this from a hotspot from my phone. I mean, both of these devices. So this is this, I'm actually shocked it's working at all. Of course, right now it's fine. And I really want to make this class happen today. But we're on it's unstable situation. Oh, okay. I'm cutting it. Someone's saying I'm cutting in and out. Yeah, I'm not surprised. Like, this is not a good electronic situation. So the reason I'm bringing that up, like, maybe the power's been off in my house for like an hour. I don't, which means the internet as well. It might come on at any minute. It's not whatever. I have no idea why this just happened, but it's happened. Um, the reason I'm saying all of this is these two classes are important enough. Um, I would definitely recommend if we lose each other or it goes in and out or whatever, please watch the video from the other class. I will post that in your Google Classroom as well. Like, um, just please be aware. Like, I did cover everything I wanted to cover in the other class. I mean, the an hour ago. And you get my point. Just be aware if I lose you or you lose me or this all is spotty or if it just becomes too hard to bear on your part, just please watch the video from the other class. Um, which I will post. But in the meantime, well, let me get going here. All right. In the meantime, oh, sorry. Yeah, see, it's all. Yeah, it is very unstable. Okay. In the me yeah, yeah. Hold on. Okay. Um, a couple of notes. There there are still a few of you, like very small hand of a few of you that still have not gotten an exam back from me. That again, that is not personal. I'm just acknowledging again. They're coming. They're almost all. Most of you have. Thank goodness. Most of you have gotten your exam back. There's a few of you who have not. It doesn't reflect anything on who you are if I haven't gotten to yours yet. And I'm almost done with them. So you're going to get them in time. You'll get them in time to do whatever you need to do for the final exam. Um, but about the final exam, oh, please remind me. Yes, okay. Regarding the final exam, can you remind me, did you, your lab in this class, your lab is on Friday, or please remind me. Oh, yeah. Oh, yeah. Where? I'm really cutting out. Yeah. All right. Again, if this just becomes too impossible to listen to, just forget it and listen to the tape of the other class, except I don't know what to say. The power may come back. But when your lab, can you remind me, you have Mercedes for lab on Friday, is that correct? You have lab Friday. Yes. Okay. Okay, thank you. Um so I will confirm and make sure with Professor Talley, but that will be an opportunity. Wait, I'm sorry. And what time does that lab end? Or what time is the lab on Friday? Okay, okay, it's in the morning. Okay, okay. So yeah, so you will that last period will be an opportunity to prepare for the final exam. Whether that means going through the practice documents, in groups, or whether she talks about the practice documents, like that's sort of all. Oh, you already did. Oh, wait. Oh, I knew something was confusing me. Okay, thank you. Oh, because we don't have lab this week. All right, you did already have. Okay. Oh, that's right. I knew that. I'm sorry. I'm sorry. Okay, okay, okay. Well, all right. So different speech for your. Okay. So here's what I want to alert you. I mean, she's and I have been in communication. What you did with her is useful and relevant. I remember now you're that section. What you did with her is useful and relevant and applicable to your final. However, she may have alerted you and you may have noticed um, I've also released another document in the Google Classroom like this morning. Let me try to be clear. The document that you went over with her last Friday was the final exam that was given last year, like 2 semesters ago or something. However, the exam that was given last semester, I just released this morning, and they overlap in a big way, but there is a significant difference between the two. There's a place in which they don't overlap. Something that I started last semester that we might do, she might have warned you about this. It is possible that one of your problems on your final exam, it's possible that one of your problems will be you'll be asked to redo the weakest problem from your midterm, like do it better, for a new score. That is possible. That is not, but that's why I want you to look, at the new document I released so that you can be aware of that possibility. I may be able to confirm, well, anyway, it's possible that one of your problems will be a redo from your midterm. It's possible that that would be a requirement. It, it's also possible that it might be a choice. I am not trying to keep you in the dark. I'm just honestly not sure yet because there's advantages and disadvantages. So the first thing I just want you all to be aware of is that for your final exam, anything is fair game from the two documents that are now existing in Google Classroom. The one that you went over some of with Mercedes, the one from last year, and the one from last semester. Anything in either of those two documents is fair game possibility for your final exam. I mean, your final exam most likely, again, will be two problems like your midterm that involve some kind of choice. It might be that one of them is required and then one you have a choice, or like I don't know, but there'll be some degree of choice. There will probably be two problems, and one of them might be that you redo something from your last exam. You should be prepared for all possibilities. Couple more notes on, and stop me if this is not making sense. And again, this speech is basically the same speech I gave in the other class, so you can watch every YouTube. But if I ask you to redo a problem from your midterm, that is in part because I think that's because I took so long with it. I want it, all of your patience and your work on your midterm to like be worthwhile and to go somewhere. So, and because, and if you're just finding out now that you didn't do as well on the midterm as you wanted to or something, I don't want that just to be um, a crash, thud, shock to your system that you can't do anything about. So that's like part of the reason. There's other reasons too, but if that's the case, if and I know there's still some of you that need to get yours back, you will get it back in time to do this. I mean, it'd be a close call, but if I ask you to redo one of your problems for the midterm, that does mean redo it. It means you're doing a newer, better draft. It means that you're rehanding it in from beginning to end. If anywhere that you lost points or that you have to fix something, hopefully, but I mean, of course, you can text me or email me, or if you can't read my handwriting, et cetera, et cetera. But anywhere you have to fix something, then you'll fix that and do it better this time. But anywhere else where you got things correct, you're still redoing them. Like you don't just hand in an adjustment or a correction. You hand in the whole problem anew. So it's like a better draft of the problem. It's everything that was included before, including everything that you did right, plus correct, plus a better version of anything you did wrong. I hope that's clear. Stop me if that's not clear. That's if you're redoing a problem for your final exam. And again, I do understand that some of you are waiting for a long time for that. And again, the fact that you're waiting a long time to get your midterm is partly why I might do that, because I actually think that makes it more fair in the long run, not less. But maybe not. That's one thing. The other thing you should be aware, and I'll get to this in a minute, is at least in one of those documents, if not both. I mean, I'm pretty sure in the document that Mercedes, that you accessed during your lab, and also I think the document that I just released, you'll notice that there's a true false section. Well, that's unusual for us after 2 semesters together. There's a true false section on your final exam. Again, it's not 100% promise that that section will be there, but it's pretty likely that it'll be there. It might be a choice. You might be choosing whether to do the true false section or not. If you choose the true false section, there are advantages and disadvantages just to be explicit about. The purpose of it, and again, stop me if you can't hear me at all, or if this is all just pointless, but the purpose of the true false section, and it would be like half of your exam. It's kind of unexpected, but if you choose to make half of your exam this true false section, the purpose of it is that is how. Oh, I see this thing in the chat. I'll get. Oh, no problem. Sorry, no problem. If you choose to do the true false section, it's the reason it's there is these last couple of classes, like the last class we just had Wednesday, today, once I get rolling, and Wednesday, I'm trying to do the last conceptual content of all this material, the material that I get very excited about, that I think makes your 2 semesters of physics really worth it, honestly. All the material that comes out of Gauss's law, that comes after the Gauss's law homework, the material that for which you don't have any homework expectations, it's all it's conceptually challenging. I want to be clear. I don't expect you to know how to solve quantitative problems with this stuff. It's hard enough to even follow what I'm saying, and I'm going to be saying it somewhat quickly once I get rolling. So the purpose of the true false is a way of assessing your understanding of the concepts that I'm doing, like in the last 3 days of class, concepts that put together all the stuff from the prior months. Why am I telling you all this? I'm telling you, on the one hand, once I start talking again about the physics in 10 minutes, I'm going to be a little bit jumpy, and not jumpy, but I'm going to go a little fast, and it's kind of intense concepts. So just know that what you're looking for is to understand the concepts. You're not looking to have to do a lot of quantitative deduction, derivations or anything like that. And it might be advisable for you to take out the true false section from one of those documents and have it in front of you while I'm talking today and Wednesday. If you follow along while I'm talking, especially on the very last day, Wednesday, that true false was originally actually meant to be it was designed to almost be a way for you to follow and pay attention and track what I'm saying in the last couple of days. So you're welcome to do that. It is not cheating to have that true false thing. And on Wednesday, I might even try to, as I go, signpost and say, oh, and this relates, there's a question about this somewhere in whatever. So I would encourage you to do that, to try to follow what I'm saying. I mean, take notes, but try to follow what I'm saying with regard to the true false in front of you. If you choose it on your final exam, of course, the advantage is that you have to do a lot less work. Like you don't have to show work. You don't have to do derivations. You either know it or you don't. That, it's like less stressful in a way to some of you. That's the obvious advantage. The disadvantage is there's no partial credit. There's no, I mean, it's cut and dried, and your chance on each question is 50-50. So, it can be a gruesome, risky thing to do. I'm not trying to set you up for failure. I want you to be aware of the risks if you do it. But it's designed to capture the conceptual content of this last material. Okay, so your final exam could be any combination of the true false of a problem from the midterm or of the E field problem that I think you sort of already went over with Mercedes. Could be any of those. Lastly, and I think Mercedes mentioned this, or one of you mentioned to Mercedes, a couple of people have noticed that in recent semesters, anything that you do with circuits seems to be very explicitly covered in the lab, but not at all explicitly covered by me in lecture. That is true. That's been brought to my attention. Thank you. So I can at least promise you that on your final exam, at the very least, there will be a way to choose your way out of the circuits. If you're not comfortable with circuits, I mean, again, I think there was like an MSRC review session about that. Like, there's ways to get comfortable with circuits, and hopefully you did understand them in lab and all of that. And I mean, the lab is part of the course, blah, blah, blah. But I know that I never really talk about them these days. So there will at least be a way to choose your way out of having to do circuits on the final, if that makes some of you more comfortable or put some stress to like you can make studying circuits your last priority. Put it that way. I'm not saying they're fully eliminated, but they won't be, they definitely won't be a requirement of the final exam. Okay, I hope that's clear. Okay. So that's all my notes. Oh, and finally, logistically, I hope this is clear. I think it was in Google Classroom, but the exam itself will be posted no later than 8 p.m. this coming Friday, right? Because that's our last day of classes, or Thursday's our last day of classes. So the exam will be posted no later than 8 p.m. this Friday. Then it'll be due back, just like the open universe, take home, all of that. It'll be due back by midnight of Tuesday of next week. Tuesday the 20th. Um, same expectations and formatting and all that as there always have been in physics. And you can still, I think I've mentioned this before, within reason and without, overwhelming me. Again, I'm behind. Some of you are behind. There's compassion, hopefully, in both directions, i.e., if you still want to hand in old stuff, old homeworks of this and that, you can do that until the last day of classes, which I'm understanding to be this Thursday. You can do that. Don't hand me in a whole pile of a million things at once. That just would be bad form and wouldn't serve you well. Prioritize more recent stuff over less recent stuff. And please don't ask me to start getting into new realms of feedback at this point, because it's not realistically going to happen. But if you have old feedback or old things that you feel that you are in a position that you could revise for more points, sure, you can do that by the end of this coming Thursday. I hope that's clear. There's one other thing I want to say about all of this logistics. Oh, finally, again, many of you had me last semester, so you sort of know this, but I just want to make, I always sort of fall apart and fall behind at the end of the semester, especially this year. I've had medical issues, and some of you know, blah, 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 blah. And they did sneak up on me more than I expected this semester. And I do apologize. I thought last semester was going to be the tough medical semester, and then this semester would be fine. It was a little bit actually the other way around, whatever. Um, um, the compassion will go in both directions. Believe me, when it comes time for final grades, which is here's now my point about how that works, especially if you haven't had me before. Your final exam is due to me Tuesday, the 20th. Okay. Then your final grades are due to CUNY for this is true for every, class. Final grades are due to CUNY first, like 10 p.m. or 11 p.m. on Tuesday, the 27th, the day after Memorial weekend. That's when grades are due. You might guess, or you might know from experience, I don't submit my grades late, but I don't submit them early either. I don't submit them before that day. Generally I submit them the day they're due, Tuesday the 27th. I cannot submit. None of us can submit one grade until all of our grades are ready to go, at least for each class. It literally is not a possibility. So none of my grades get submitted until all of them are ready. So please don't, so hand in your final exam Tuesday the 20th, it will be a week of me being in the cave, not until you get your final grades. I will not really be in a position to do much individual helping of people during that time. I'm just trying to get the whole group numbers back. What you should know is I did this last semester and I'll do it again. Somewhere before Tuesday, I will release a spreadsheet with all the data, and the formulas, like all your grading data and all how it got calculated. So you'll see full transparency before the grades go to CUNY first. You'll see your final grade, you'll see your final exam grade, you'll see how the whole thing was calculated. I mean, in principle, I mean, it's not like I'm changing the rules or something, but you'll see it all. So if there's any issue or shock to your system or question or inquiry, you should look out for that. Like the day before, like Monday, Memorial Day or something like that. You should look out and you will get an unofficial release from me. And if there's an issue, let me know quickly. Um, you understand what I'm saying? In other words, I'm not, you'll have a moment to see what's what and assimilate the reality before it gets released to CUNY first. Okay. So hopefully that's clear. Again, we still have one more class after this, but I just want all these things to be good. Again, lastly, I know I say this like every time, but just at this point in the year, um, especially if I'm fading in and out. Okay. This is just, again, if you, I think I say this on the very first day of class, but just to remind you now, if there's any kind of quick question that you want in the next couple of weeks, if there's any concise, quick way that I can lower your stress level or lower your anxiety, doesn't really seem like I'd be the appropriate person to do that. But if you could text me a question that would take you longer to write the question than it would take me to write the answer, like, did you say circuits are on the exam, or do you still have my exam, or what time is the exam, or something? If you can ask me a quick question, feel free to text me. If I can in any way, make your life easier with a quick turnaround, text is faster than email. Feel free. But if it's like, or even if is it possible to make a phone appointment with you for 15 minutes, whatever, then yes, like I can make the appointment through text. It might be easier than through, anyway, you get the point. So feel free. Okay. So I think, I know I'm still on the, what do you call it? I'm still on the tether here thing, but I want to start. Can I start talking? So do we sort of understand what's about to happen in the next 2 weeks? Like, are we good for me to go with the last bits of physics? Okay, thank you. Thank you, direct chat person. All right, that's one, but I'll take it. All right. These equations that are on the board here are the equations I'd like to get to today. I will get to today. I don't expect you to already know them. I'm going to somewhat quickly explain the conceptual content of these really important historical equations, all about magnetism. So let me um, back up and remind you of where wow, the lag, there we go. Okay, the lag is, if this is what you're experiencing on your side, my God. My cork. Okay, there we go. So, quick review of what we established. We are talking now about the magnetic field. Okay. Um, we've been talking about the electrostatic field for a while. Now, in these last few days, we're talking about the magnetic field. The magnetic field, we have two basic equations that we established about everything we're doing about the magnetic field is like some sort of analogy or every way in which we look at the magnetic field mimics a way in which we looked at the electrostatic field. It's all the same type of thought process, but the findings are different. So just like with the electrostatic field, we had an equation for the field itself, Coulomb's law, and then we had an equation that said what force the field would exert on a sitting charge. So with electrostatics, a sitting charge makes an electrostatic field, and then the electrostatic field exerts a force on a different sitting charge. Source creates field, field exerts force on test. Okay, same thing with magnetism. Only now what's making the magnetic field is not a sitting charge, but a moving charge, i.e., a bit of current is what produces the magnetic field, we empirically find out. So the equation, so what we have so far is two equations. An equation that shows how the magnetic field is produced. That's the top equation here from last Wednesday or last Monday. That's the B field. That law is like the magnetic equivalent of Coulomb's law. It's called the Biot-Savart law. And it says how a little bit of moving charge or a little element of current would produce a magnetic field. And it has a cross product in it, right? I'm just reviewing what we were saying last week. It has a cross product, which is like a new, which we've never seen before in a field or any kind of force function. Um, the power's coming back on. Bear with me for a second, or it sounds like the power's coming back on. Hold on one sec. I think. Yes, I think. Hold on. Tell me in like a minute and a half if I believe the. Sorry. I believe the power's coming back on. Hold on. Bear with me, please. Now tell me. All right, I may lose you temporarily for a second because I'm turning off. Are you still there? Wait. Oh, no, I shouldn't have done that. Wait. I'm muted. I did not know. Thank you. Okay, I did not know. Wait, okay, can you hear me now? Are we good now? Yes. Okay, thank you. All right, sorry about all that. All right, I was afraid that was all right. Well, anyway, now it should be more stable at least, I guess. I guess we're now okay. So anyway, magnetic field, the key, okay, the math of the magnetic field is a little harder or maybe more intimidating than the math of the electrostatic field because the magnetic field intrinsically has a cross product in it. And the force exerted by the magnetic field has a cross product in it. Um, this means that every time we do every time we compute the magnetic field or we compute the magnetic force from the field, always doing a right-hand rule. The magnetic field is perpendicular to the vectors that cause it, and the magnetic force to both of them. So the magnetic field always points in a direction that, in some sense, seems unexpected. If you have a current going like this, and you are at a displacement underneath the current, and you're asking, what's the magnetic field here at this point underneath a current going like that, right? The magnetic field here does not point down or up, nor does it point along the flow of the current. It points in an axis that is neither the motion of the charges nor the displacement from the charges. If there was current going like this, we would do right-hand rule and say the current's going like this. I'm looking at a point underneath the current, so I would take my right hand and curl it down, and my thumb would point like toward my face, away from you, and we would say, aha, the magnetic field is pointing that way, like out of the board toward my face. Totally strange, it seems at first. Like the magnetic field points in a direction that seems to have as little to do as possible with the direction that you are from the thing that's causing the field, and as little to do as possible from the direction of the flow that is causing the field. That seems really weird until you really stop and think that that is the reason it's happening like that. Like the whole point, the reason cross products now come into our life, the reason now right-hand rules come physically into our life, the reason that we're now forced to look at 3 dimensions of space is that the thing that causes magnetism is not a scalar point anymore. Like, remember what caused gravitation was a point of mass, just a number sitting at a dot in space is what caused gravitation. And what causes electrostatics is the same. It's just a point charge, a little dot of some amount of coulombs. Like maybe it's a proton, maybe it's an electron, but it's like a dot that just has a certain number of coulombs, and that creates the electrostatic field. A dot does not have dimension, and it also doesn't have direction. So what caused the electrostatic field was just a sheer magnitude. And then we would ask ourselves, well, what's the electric field like at a point over here? We would draw in our minds a displacement from the point source to wherever we were looking at and say, what is the field over here where I'm looking at? So there'd be this one vector, R, pointing from the source to where we were. And we would multiply that vector, R, by the magnitude of the charge and fundamental constants and things like that. And we would get a vector over here that was produced by a scalar multiplying a vector. And the force or the field that we would get over here pointed in expected directions. What do I mean by expected directions? I mean along the direction of R. Like if the proton is here and you were to the right of the proton, the field would point to the right. You'd get pushed to the right by that proton to which you were on the right-hand side. Like it made so much sense that we didn't even think about like the possibility that there could be any other options but that. Like, okay, but with magnetism, it is not like that because what is causing the magnetic field is no longer a scalar dot. Now what's causing the magnetic field literally is a vector of flow. A bit of current is what's called that's what kicks magnetism into existence. It's the first time we've ever seen this in physics. It's not just an object that makes this field. It's an object doing something. It's an object or a set of objects moving along a line in a particular direction. So, which we call current ultimately, right? So what's now causing magnetism in the first place is already itself a vector. And then we want to know what the magnetic field is, some displacement vector away from that vector. So we now, for the first time intrinsically have two vectors of information together producing some piece of information that's going to be somewhere in space. We have a flow going in a certain direction, and then we have a displacement from that flow in a certain direction. So in fact, the cross product, so we're taking two vectors, multiplying them together to get a vector. So mathematically, that's why it's a cross product. But physically, what that means and why the cross product always forces the right-hand rule, always produces a vector that is pointing along an axis that seems so crazy, maybe, is exactly because anything other than the third remaining axis would actually be crazy. If the vector result of the cross product actually didn't point along an axis that was perpendicular to both of the original vectors, it would be assigning extra weight, extra emphasis, extra priority to one of the two pieces of information that was producing it. What we're really saying here is if there's a current going like this, and we're looking at a point down here over here, this point in space is taking that information and putting them in a package that is attributing equal value to each of those pieces of directional information, the that and the that, right? And so in order for this package to convey or transmit or contain both directions in an equal way, it points along the last remaining axis, right? So you could sort of reverse engineer. If you're space and you see a magnetic field pointing this way, you know it's being produced by some kind of current that's not on this axis and some kind of displacement that's not on this axis. And the information gets unpacked from there. I'm saying a lot, but what I'm trying to say is that all these that the magnetic field is a field like gravitational or the electrostatic, and it follows all the rules computationally, visually. It follows all the rules of fields, but applies those rules to this interesting new case where what is kicking those rules into activity is a vector, not a point. Okay, so the magnetic field is always perpendicular to the vector that caused it and the vector of displacement from that vector that caused it. The magnetic field is always perpendicular to current and displacement from current. And the magnetic force, same idea, must be perpendicular to the current that's experiencing it and the magnetic field that the current is receiving the force from. Everything is right angles. Everything is right-hand rule. What this ends up meaning. So, okay. So technically, again, that's like review from last time, but it's like a lot. It's like again, the takeaway is this is how fields would have to work and do work when they're caused by a vector rather than a point. I mean, that is truly what I'm trying to say a million different ways. What that ends up meaning visually is magnetic field lines do not burst out of dots anymore. I mean, electrostatic field lines radiate out from points. They radiate out equally in all directions. Gravitational lines pull in to points equally in all directions. Magnetic field lines, if they're to be as symmetric as possible, given the situation that's producing them, magnetic field lines don't burst out of points. They're coming from lines, and they're not just lines, they're lines with direction. So what they end up doing is looping around these lines. Like, again, I'm just looking at the time. Like, again, I'll try to say this one more time. If this were a current going like this across the page, and you were to look at a point underneath it, right? Right-hand rule says current going like that, or QV vector going like that, R going down the page. So the thumb would point toward me. So right here at a point underneath flow, right here, the magnetic field would be pointing to me. But if I did the right hand rule above the current, if I do that, if I do that, then I curl my fingers up. So then my thumb would be pointing out toward you. So below the line, it would be, if the line's going that way, um, the magnetic field would point toward me. Above the line, it would point toward you. If you did the right hand rule out in front of the line of flow, the magnetic field would be pointing down. If you did the right hand rule behind the line of flow, the magnetic field would be pointing up. I mean, if you just try the right hand rule at all various points nearby some vector of current flow, what you find is the magnetic field loops around the current. That's the second thing I'm trying to say, the thing in white on the board, that magnetic field lines don't burst out from points, they loop around arrows. Magnetic field lines are always closed paths. Magnetic field lines are always closed paths. Again, because so the picture of the simple of just a straight line of current would be a bunch of concentric circles of magnetic field spreading out and out from that axis, as opposed to radial lines spreading out from a point. Magnetic field lines do not have sources and sinks. They don't start at positives or end at negatives or go off to infinity or anything like that. They literally always close themselves and form loops. Again, because they're being caused by arrows, not by points. Okay, so that's a truism to take away from last time. So then, given that, let's say we're following the thought process that we follow with electrostatics, and let's say, all right, now we know what one simple current would make magnetic field lines that are circles around it. What if we have a whole bunch of currents in a space? What if we have a continuous distribution of currents and we want to know what the magnetic field is at a point over here? That's like what happened with us with electrostatics. First, we figured out the electric field from a point. Then we said, what if we have a whole bunch? What if we have a continuous distribution of points, like a line of charge or a plate of charge or a sphere of charge, like the whole Gauss's law homework? We started saying, what if we had a whole bunch of continuously distributed charge and we wanted to know what kind of field that's producing? Like, what would we do? What we did was we considered the idea of flux, and we started considering the flux through closed surfaces. So the question is, can we adopt that same strategy? It's a rhetorical question. Can we adopt that same strategy of considering flux and closed surfaces when it comes to magnetism? Well, it's a good idea. Let's try it. The thing is that when we try it, we find that any close, well, remember, I'll just remind you for a second. Well, no. Remember, with Gauss's law, the idea was any closed surface you pick, the net electrostatic flux out of that closed surface would always be fully determined by the charge enclosed by that surface divided by a constant. I mean, the law, I write it again in a couple pages. I'll show it to you again. But Gauss's law is flux equals charge enclosed over epsilon naught, right? But here, so in other words, the total amount of charge points within a container determines the total number of E field lines coming out of that container. We're looking for something like that here with magnetism. Can we, construct a similar law? Well, we can, except that on the right-hand side of this law, we're going to get zero every time. Now in fact, that's a law. It's called Gauss's law for magnetism. No matter what, now this is interesting. Let's think about this for a second. Like, why would that be? Because what we're saying here is no matter what closed surface, no matter what shape of container you pick anywhere in the universe, you just pick a container and you ask, how many magnetic field lines are coming out of this container? Like, how many net lines are net coming out? Meaning, if I see a line coming out, I'll count it as one. But then if I see another line going in, I count that as -1, if you know what I mean. Like, we want to know what's the total amount of outs minus the total number of ins. Well, with magnetic lines, no matter what you do, every time a line comes out, like say you make a container over here and you've captured a bunch of little currents inside your container. So the currents are making magnetic field lines. Okay. So there's lines coming out of your container. Okay. But the thing is, if they're magnetic lines, they necessarily form closed paths. So any magnetic line that does come out of your container is going to go back into your container somewhere, somehow later. Do you see what I'm saying? And stop me if you don't see what I'm saying. But I'm saying, and that's not true with electricity. Electricity, any line that goes out will keep going until or I mean, or certainly can keep going until infinity or until it hits a negative somewhere else. But magnetic field lines don't keep going. They come back always. So the net magnetic flux out of any closed surface is always zero. A way of saying that in English that you may have heard either in another science class or maybe even in a science fiction, like there's a lot of science fiction written about this sort of almost cliche, which is there's no such thing as a magnetic monopole. That's the English way of saying this law, Gauss's law for magnetism, meaning there is no elemental object whose existence produces a radiomagnetic field line. Like there is for electricity. It's called a proton or an electron. Those are monopoles. Those are single poles that produce lines that come out of them. And a proton is a single pole. Lines will come out of it. An electron, so it's like called a source. An electron is called a sink. It's a single pole into which E field lines will come, right? There is no element like that out of which magnetic field lines just radiate. There are only currents around which magnetic field lines loop. Okay, I don't know any better way to put it than that. There's no such thing as a magnetic monopole. The total flux through the net magnetic flux through any closed is always zero. Okay. Therefore, so that's interesting, but that's not going to help us. And it is interesting. It's a law, but it's not going to help us compute magnetic field from continuous current distributions. How do we do that? Like, what is the magnetic answer to Gauss's law? Like, what is the useful version of Gauss's law for magnetism? Well, it's called it's called Ampere's law. I'm getting ahead of myself, but it's called Ampere's law. And what Ampere did was Ampere said, okay, look, if this is a problem, if magnetic field lines themselves are closed paths, then that means we're not going to get any insight really, or any specific quantitative insight into magnetic fields by looking at closed surfaces. Like we just covered that. If we look at closed surfaces, lines are going to come out of them and then go back in. Like that doesn't do anything for us. So why don't we look directly at closed paths? Like Ampere comes along and says, let's build a law, like let's conjecture and then verify if a law of the same character as Gauss's law can be done, but instead of focusing on closed surfaces, let's focus on closed paths. So Ampere conjectures and then verifies that there is a law, we can call it Ampere's law. Sorry, okay. It's like the analogy or the analogous counterpart to Gauss's law. Gauss's law, again, is a double integral, right? It's a double closed integral, or it's a closed surface integral. Gauss's law was. So that's on the top in white, right? Gauss's law says for any closed surface, the total number of E lines coming out of that surface, the total effect of E field coming out of any closed surface is fully determined by the charge enclosed in that surface, within that surface. That's what Gauss's law said. I want to remind you of an English. Now, again, the more you think about, if you think of E field lines like water or something, the more you think of E field lines like water or some thingy thing, the more Gauss's law starts to make sense and almost seems self-evident. What Gauss's law is capturing a sort of recognition about basic space that all of you always knew, but you just maybe didn't think about or didn't think that it mattered. Or so, well, I'll say that I always knew, but I didn't know it mattered or know that I knew it, which is this, which is the part that it says in blue right underneath. And I believe I've said this to you in English before, but I'm going to say it again now. A closed, well, let me back up for a second. Regions can be closed or open, right? Like any kind of region, a one-dimensional region of space, a two-dimensional region of space, a three-dimensional, well, that I don't know, but they can be closed or open. Like here's a line segment, like a piece of string is an open segment. What do I mean by open? I mean it's not closed. What do I mean by closed? I mean if I took that string and bent it around itself so its ends touched, then it'd be a closed, like this is a open path, this is a closed path. What's the difference? Can you tell? A closed path is one where if you go in a certain direction, if you're like a mosquito in a closed path, if you walk in a certain direction long enough, you'll end up where you started, even though you never actually change your direction. That's what it means to be in a closed path, right? You automatically, it forces you to do a round trip, basically, right? So paths can be open or closed. Similarly, surfaces can be open or closed. Like this, like a piece of paper or something is an open, a piece of paper is an open surface. It's open because it's not closed. What would it mean for it to be closed? It'd be closed if all of its ends, all of its edges were touching one another. And so then if I were able to like wrap a box with this paper or a globe with this paper, if this paper wasn't just an area, but became the surface area for some volume, I'm going to look at that chat in 1 second, then we'd call it closed, right? So just know, I'm going to look in the chat, but just notice two things. First of all, regions can be open or they can be closed. It's closed if you can go in the same direction for long enough and end up back where you started. Like if you can end up back where you started without changing direction, then the region is closed. That's number one. Number two, I know there's something in the chat. There's something I want to get out of my brain before I lose it. So number one, regions can be open or closed, whether they're one-dimensional or two-dimensional, they can be open or closed. Okay, I'll leave it at that for the moment. Let me just look in the chat. Oh, there's a lot of things in the chat. I'm sorry. Hold on. Wait, am I still muted? Oh, that's clever. That's interesting. What if you go around the paper to the backside? Right. But if you do that, then okay, that's interesting. I'll say this quickly. I mean, that is a fun question. I don't want to get too, but if you were able to do that, if you're literally able to go around the paper to the backside, that would mean that you crawled like down one of the edges of the paper, right? Which means that then we're counting those edges as actually part of, like, then that means that really that paper is really a rectangular prism, just very, very squashed, right? And that's fine. I mean, but that's not what I mean by a piece of paper. When I say piece of paper, I mean like a two-dimensional region. If once you're allowed to crawl on the edges, then what you're talking about is the surface of a three-dimensional box, and that would be a closed surface then. Do you follow it? Like, I'm not dismissing what you're saying, but then you're by doing that, you're back in the other example, if that makes sense. I don't know. So, but you know what's great about that question? It reminds me of the thing I couldn't remember to say a second ago. Let me know in a minute whether you buy that or not. But what I am implying is you could take a region of space, like a one-dimensional path or a two-dimensional area, and you can close up that region. But in order to do it, you have to bend or warp it into a higher dimension. Like there's no way I can take a one-dimensional segment, like a line, there's no way I can turn it into a ring without having a second dimension within which to work, right? So, but even when I bend a path into a ring, when I make it into a ring, it's still, the region is still one dimensional. Like we still measure perimeters or circumferences or whatever you want to call it in meters or inches, like not square meters or inches. The ring is still a one-dimensional path, but it exists in a two-dimensional space. Just like a surface area is still an area. It's still measured in square centimeters, but it exists. It requires the existence of a third dimension in order for it to be its thing, which I think is sort of implied by your question, and it's an important observation. So where am I going with it? I don't. Let me know if I didn't answer your question, but I think I did. But okay,
No, you did. Thank you.
Oh, okay, thank you. Okay, thank you. All right. So that's like a bit of sort of abstract geometry about the nature of space. But how that's being used by Gauss's law and then by Ampere's laws, Gauss's law is basically saying, yeah, look, any closed two-dimensional region of space, any closed surface is necessarily the boundary to a unique volume within. A closed area, a closed surface is the boundary of a unique volume enclosed by that boundary. Like once you say this is the shape of my container that I'm picturing, we all automatically know what's inside the container in the volume of the container and what's not. So Gauss can come along and make and say, look, the total number of lines coming out of a container is out of the surface that constitutes a container is fully determined by all the amount of charge points enclosed by that container. The left side of Gauss's law is a two-dimensional reference, and the right side is a three-dimensional reference, is what I'm trying to say. And it works because one specifically is the boundary to the other. He can say charge enclosed and assume that we all know exactly what he means. We know which charge is inside and which charge is out because once you've defined this closed surface, you've automatically defined the boundary of a unique volume. So Gauss's law, and so the whole premise is that field lines only exist because charge points made them in the first place. So if you know the number of charge points inside a container, you know the number of field lines coming out of that container is all he's saying, just like if you have a sprinkler or a spigot, a sprinkler that shoots jets of water, we're just saying if you know how many drops of water come out of that sprinkler every second, then you automatically know how many drops are hitting some surrounding tent every second, no matter what size or shape that tent is. The water that hits the tent is fully determined by the sprinkler heads that cause the water. That's all we're saying in a way with Gauss's law. It assumes that a closed surface is the boundary to a unique volume. Well, Ampere comes along and says, all right, I'm going to use that same type of reasoning. I'm going to just bring it down a dimension to understand magnetic lines. Magnetic lines are already closed loops. So a closed loop, it says in blue down here, a closed one-dimensional region of space is the boundary for an open two-dimensional region of space. Like this ring right here is the boundary to the disk within. You see what I'm saying, right? The disk within is bounded by the ring, but it's not closed. I mean, in other words, there's a difference between bounded and closed. This disk within is open because I didn't close it up. I didn't make it into a package or a container. It's an open area, this disk within, but its boundary is the ring around it. Okay? So Ampere says, yeah, I bet you, and he turns out to be correct, largely correct. Ampere says, yeah, I bet if you walk around any closed path through anywhere in space, the total amount of magnetic field that you'll pick up in that closed path, notice single closed integral now, not double. If you walk around a single dimensionally closed path and add up all the magnetic field around that, I bet, says he, that it will be fully determined by all the current enclosed by that path. And he turns out to be right, at least for steady currents. The only question now is, what do I mean by enclosed current? Like, it seemed sort of clear, comparatively clear, when you have a container, charge enclosed means all the charge enclosed in the volume bounded by that container. The volume contained within. What do we mean by current enclosed? Well, by current enclosed, what we really mean is the current fluxing through, passing perpendicularly through the area enclosed, the open area that is bound by that closed path. Again, I know this is like, it's a little bit heady, right? Again, you may want to start looking. This is why the way I'm testing you on this, like I want you to know this because it's ultimately, weirdly, like the most exciting stuff in physics, at least to me, in a strange way. But it's strange, right? So I'm not asking you to solve problems, I'm just asking you to understand these concepts. Hence, there's true false questions like about all this. Or I'm going to keep talking, but just again, just to so you don't think I'm just talking in space. I mean, I'm talking about space, but all right. So current enclosed means the total amount of current passing perpendicularly through the area enclosed by the closed path. So a closed surface always bounds a unique volume. A closed path always bounds an open area. I can say open now. I can say open because with two-dimensional things, I can tell the difference between open and closed. Quick, like notice there's a slight word change here. I said unique in the top blue statement. Now down here, I'm not saying unique, I'm saying open. And why is that distinction? Because we live in three dimensions of space, evidently. And the thing that I was saying before, and that Annie touched on with her question is once you're closing up a region, you must be going into the higher dimension. Okay. Like a closed surface actually occupies three dimensions, even though it is an area, and a closed path actually occupies two dimensions, even though it is a path, right? So, so with volumes, I can't, no, but we have no access to whether volumes are open or closed. If they were closed, they'd have to be closing. I'm not saying they aren't. I, but if they are, if a volume is closed, that means it has to be closing up in the fourth dimension, which right now I have no access to the fourth dimension. So I don't know whether volumes are open or closed. That's why the volume inside a container is just a unique, unambiguous volume. I call it unique. But the area inside a disk, I mean, the area of a disk inside a ring, oh, I can say that is open. I could picture what it would be like if it were closed. It would be bent, and it's not. Okay, anyway, so Ampere's law is like the lower dimensional version of Gauss's law. Okay, so now we've established, and that's how we calculate magnetic fields. There's yet one more law that I want to tell you with 11 minutes left. Just one more. You're being very patient, or you're being very something. Um, well, okay, so I said that. Oh, so here's a summary of what I just said, if it makes it any more visually clear. I'm just saying, what according to Ampere's law, if you want to know the total amount of magnetic field around some yellow here, like closed path, some loop, the magnetic field is fully determined by the total amount of current that passes perpendicularly through the area enclosed by that loop. Okay, so the yellow is like the left-hand side of Ampere's law. The white is the right-hand side of Ampere's law. And yes, it's a bit abstract, but it's true. And I'm trying to get you to see the connection that this is like what we do for Gauss's law for electrostatics. Yes. Wait, I don't remember what for HM7. Probably, yeah. Is seven? Is that? Yes, I guess. Sorry. Yeah, I think so. I don't remember which HM7 is, but yes, this is definitely like a question. Um, um, and the main thing is to see how this is the same logic of regions and boundaries as Gauss's law, only taken down a dimension. Um, okay, but now along we have 10 minutes, 9 minutes. Early 1800s, along comes a high school chemistry teacher in Scotland who turns out to be a very famous scientist, Michael Faraday. Now, Michael Faraday, like many of us perhaps, does not actually like grinding mathematical equations. He's not that into mathematical equations or formulas or quantitative stuff. He's very visual and he's very visual. He is the man that in some ways gives us all this content. He's the one that loves thinking in terms of magnetic flux and electrostatic flux. Because when we think in terms of flux, we just count lines, and he prefers to make intricate drawings with field lines in them and count lines rather than do a lot of analytical quantitative stuff. And he's a great experimentalist, Michael Faraday. So he says, wait a second, I'm realizing that all this magnetic field stuff is always at right angles to that which caused it. And the magnetic forces are at right angles to the fields that cause it. So he designs an apparatus. He says, what if we have a constant, this is like a bird's eye view, this picture. It's supposed to be a constant magnetic field, like sort of pointing into the lab table, right? With metal rails all around, like a rectangle of metal rails, metal rail, a metal rail over here that has a resistor on it, in it, and then a metal rod that is free to move back and forth along these rails, and a metal rod that therefore completes like a rectangle. It's like the fourth side of a rectangle. And he puts this metal rod onto the rails in a magnetic field. Now, when it sits there, it's just sitting there. Certainly there's a bunch of charges in the rod. I mean, just because there's charges in everything, there's protons, there's electrons, like there is in everything. But first of all, there's an equal number of protons and electrons, and second of all, more to the point, they're just sitting there. So they're in a magnetic field, but they don't care, and we don't care any more than you would care if there's mass in an electrostatic field. Like there's a field, but electrostatic field doesn't start exerting forces until you put a charge in it, right? So charge creates electrostatic field, and field exerts force on charge. Source charge, field, test charge. Same thing with magnetism. Currents create magnetic field, but then currents also are the only thing that experience a force, or moving charges are the only thing that experience a force from a magnetic field. So he starts moving the rod at a constant velocity, like in toward the resistor. He moves the rod toward the resistor. So now we've got QVs, like protons, going like this in the magnetic field. And the magnetic field is going into the board, as an example. So there's so cross product, right hand rule. There's a magnetic force on the charges, the positive charges, that brings them down the rod. Similarly, a magnetic force would bring the negative charges up the rod. So now positive charge starts to flow down the rod, and the rod is attached to metal, which is attached to metal, which is attached to metal. So once the rod is moved at a constant velocity on purpose by Faraday, once he starts moving the rod, electricity, an electrical current is generated, is induced in this rectangle of metal. And if he moves the rod the other way, electricity goes the other way. So this is a very big deal. You've heard of it. Well, right. Okay, I just said it. Because F equals QV cross B, right-hand rule, the charges will move through the metal, and then the charge will move around, and we have an electrical current. So that means electrical potential and electrical current are now created without a chemical battery. Like suddenly we have an electrical circuit, just like you use in the lab, but there's no voltaic cell, there's no power supply, there's no chemistry, there's no battery. There's just mechanical energy suddenly prompting. There's mechanical energy being added through a magnetic field that's suddenly prompting electricity. So this is called electromagnetic induction. And of course, you've heard of this. And this thing that he's made here is a generator. Generator means a way of generating electricity, electric potential, voltage, and electric current without the use of a chemical battery. Big deal. I mean, not sarcastically, this is a big deal. This is the Industrial Revolution right here, this generator. I mean, Michael Faraday is like, and he doesn't like math. Just for the record, for those of you who don't like math, he doesn't like math. He's great with his hands. He's great with his visual mind, and he's not a perfect. He's a high school chemistry teacher, but he's a great scientist. I shouldn't say but, and he's a great scientist. So he makes this generator. Now we've got 4 minutes left. Yes, the industrial applications of this are beyond belief, but I'm actually interested in the theoretical implications, which are equally beyond belief. This apparatus, so bear with me for like 4 minutes, 3 minutes. This apparatus, it makes sense. Once he decided to design it, he did predict and correctly predict what the result would be, because the result of current flowing around follows from everything we've already said about magnetism, Ampere's law, Gauss's law, Biot-Savart law. Like once we understand that magnetic fields and forces work at right angles, something like this becomes possible. So it's a great application, but in and of itself, it seems explicable, not shocking. What's shocking is that, well, 3 minutes. What's interesting before shocking is that Faraday, as I mentioned before, loves to think in terms of flux. Flux is more visual to him. Flux allows him to think in terms of field lines, right? Like I'm writing these things in terms of integrals and stuff. It's not the way he thought about it. But he likes to count field lines and think about it in terms of flux. So he looks at this apparatus and he says, actually, what's happening here is electric field is being induced in the closed path bounding that area, that open area through which the magnetic field is in. And when I moved the rod, he says, what I was doing was changing the area of that rectangle by, right? I mean, he was by moving the rod, he's changing the area bound by the closed path. And since flux is stuff times area, magnetic flux is magnetic field times area, Faraday says it looks like I changed the flux there through changing the area. I didn't change the magnetic field strength, but I changed the area. Therefore, I changed the product of flux. And by changing the flux in time, I got electricity in the closed path bounding the open area. That's the way he thinks of it. Okay, fine. We can say, well, we don't want to think of it that way. But the reason it becomes useful to think about it that way is that then it turns out that in any other apparatus that he or anybody else designs, if in any way you change the magnetic flux in time through an open area, automatically an electric field is induced in the closed path bounding that area. In other words, even if he had, when he then, and I know we have 1 minute left, when he tries a different version and just pumps stronger magnetic field through the area without moving the rod at all, but just pumps stronger magnetic field, the same thing happens. And that cannot be explained by prior laws if you think it through on your own time. Like there's no reason just making the field stronger. If nothing's moving in it, there's no reason that there should be a current, but there is. So what he discovers is a new and final law for us that sort of parallels the other laws. That there's an electric field induced in any closed path if the magnetic field through the area bound by that path changes in time. E dot dl, path integral of E dot dl equals the negative of d dt of of surface integral of magnetic field. The right side is not closed. That's not an accident. It's open. I'll just say this. So this is again a 1D to 2D law, like Ampere's law. I know it's 420. I'm just saying the final law is Faraday's law, which says anytime you anytime you change the magnetic flux through an open area, it will induce electric field through the closed path bounding that area. So that's enough for today. You've been very patient, especially with all the glitches and stuff. I will see you in 2 days for our final class. I hope you're there. Thank you. Yes, have a great day, everybody. Hold on, and hold on. And don't wait.
Bye, thank you.
Thank you very much. Thank you very much. Okay.